All right, so welcome everyone. So this week I want to go back. This is Legion week. I want to go back and clean up some of the stuff that I did not explain particularly well in the last meeting. So I want to start back with this perform mapping operations. The goal of this talk today will be I want to go through the scheduler here in just a little more detail to explain some more of what's going on and some more of the invariants that I hand waved a bit through the last time, and then the main thing that I want to get into today is showing you a little bit about how we do calls back to the mapper, so you can actually understand what that looks like and sort of the model for how the runtime thinks about talking to the mapper and asking the mapper to do various things for it. And there's obviously some mapper calls in here that we do in this perform mapping operations. So once we go through this in a little more detail, then we'll look at where some of those invocations to the mapper go and how mappers handle those and send responses back. But before we jump to the mapper, I did want to talk through this perform mapping operations function in a little more detail, because this is sort of like the main scheduling loop, but it is very important. So I actually want to go through this not quite line by line, but actually talk about some more of the details with it. If you remember, this is the call that gets called to actually do the scheduling for tasks. So when tasks have had all of their mapping dependencies satisfied, let's actually just do a brief reminder of like some of the things that set up the call to this perform mapping operations, just to sort of show you what happens. Let's see. So up here, let's see. Where's my search function? Oh, I need to actually be in there we go. Yep. So if you remember, let's see, we had these activate context calls, right? They come whenever a context has, not enough outstanding map tasks, right? And anytime that you get a new active context, right, coming from the context we looked at the last time, that will, say that we have a new number of active contexts, right? And if we're now activating this context for the first time, right, we call this increment active context call. And the invariant to call the scheduler, right, whether the task scheduler for this particular processor manager is enabled or not, right, occurs whenever the first time you either, in order to be running the scheduler, we have to have at least one active context and at least one active mapper. And we'll talk about what an active mapper is. But remember, an active context just means that, there's not enough outstanding map tasks or tasks that are mapped on that particular context, and therefore it needs to do more work, right? And if that's the case and we don't have our current scheduler enabled, we set the bit saying that our scheduler is enabled, and then we launch the scheduling task, right? And we increment our total number of active tasks. And this all happens guarded by a lock. Like if I go back and look at where increment active context was actually called from, you will see that we are holding this Q lock here, right? And that's actually the thing that protects the state that that we're guarding in here. So anytime you're incrementing either the active context or the number of active mappers, you're going to be holding this Q lock on the processor manager, which effectively protects all of your data and state for this particular the scheduling of this particular processor. Now similarly, like I'm also showing this add to ready queue for this task hop. This also will increment the number of tasks that are active for the particular mapper associated with this particular task, right? So this task is a mappable object, which means that it has a mapper ID, right? So when the user launched this task, they gave it a mapper that is going to be responsible for handling all of the mapping for this task, right? And that updates this mapper state object. And I'm going to show you this mapper state object over here, right? So for every mapper, we maintain a list of all the tasks that are in its ready queue, right? Tasks that are ready to be mapped that mapper might want to talk to about. We're also tracking whether the application or whether the mapper has asked us to defer mapping. We'll talk about that a little bit later, and we'll show what these other things are over here in just a minute when we walk through the scheduling task. But the main thing here is this ready queue, tracking all the tasks that are ready to be mapped by this particular mapper on this processor. Okay, and so again, like, and you see, like, if the ready queue is empty before, right? Then we don't have or we have a deferral event, right? We might increment this active mapper, and increment. If I can spell, still cannot spell. right? And again, like the invariant for launching the scheduler task is that you have at least one active mapper and at least one active context, right? And as long as you have each of those two things and you don't currently have your scheduler invoked, then we do whatever is necessary to launch the scheduling task, which will come around and call back in and call this perform mapping operations call to actually perform any mapping. So, if you have active mappers, which means you've got tasks that are ready to map and those mappers are ready to do it, but your contexts are all mapped, well into the future, then you don't need to do your scheduler. Similarly, if you've got like a bunch of tasks, or if you've got like, a bunch of contexts that are active, but there's no tasks that are ready to map, then there's no reason to call the scheduler either, right? Because, there's nothing to do any mapping for. So you need to have both of those things be non-zero in order to run the scheduler, right? And of course, the first time any one of those things state changes from zero to not zero, that's when you do the check to see if you need to launch the scheduler. Okay, so that's sort of the state which comes into this perform mapping operations, right? And then this perform mapping operations gets called by the scheduler, whenever those two state variables are both non-zero on this particular processor. So let's actually look at what happens here. So the first thing we're doing is we're actually just grabbing our set of current mappers. And you notice this is a different lock here to protect this data structure, the set of the mappers, right? So applications can record new mappers with processors on the fly in Legion today. So this mapper data structure that we're looking into here, the set of mappers for this particular processor is variant, but it doesn't change very often. So we use a different lock to protect that. It's pretty rare that you're ever hitting this particular, any kind of races on these things. But we do protect it just to make sure we pull out the current mappers. Currently, there's no real way to delete a mapper in Legion, or at least not a well-specified one. Mappers kind of sort of live to the end of the application once they're registered. So effectively, this is mainly just protecting against like this map, growing in size during the course of the application, right? But so we effectively go through and pull out, the set of the current mappers associated with this particular processor, which we might need to talk to here. Okay, and now what we do is we're going to iterate over all these mappers that we have for our current processor, right? And the first thing and one thing, speaking of this here, there may be a performance bug here where like you actually don't need to grab all these mappers. And if you had an unusually large number of mappers associated with the processor, this is likely to be a performance bug that we'll need to fix in the future. But for now, it seems to get the job done. Most applications register at most a few mappers, and so we don't have a major issue with that today. Okay. So the next thing we're going to do is we're going to iterate over each of those mappers, right? And so we're going to get the mapper ID, which is effectively the name for the mapper. And you'll notice that it has this mapper manager object. This is going to be a wrapper around the mapper itself, which we are going to go look at today. But for now, you can just effectively think of this as the reference to the actual object, which will handle all of the mapper calls. And so like we'll go take a look at that object today and what it entails and stuff. But this is just the thing that we're going to invoke all the mapper calls on. Okay, so what we're going to do here is mapper calls are often pretty expensive, right? And so especially the call to select task to map. So what we're actually going to do is going to grab sort of the set of tasks that are ready to map and pull it off of this queue while still allowing that queue to effectively be updated with new tasks that are ready to map even while we're doing our mapper call, right? So what we're going to do is we're going to pull off a copy of the queue and it's and a potential event for when this queue is ready, and you'll see where this comes into play in just a moment. And then we'll be able to effectively like get the state of all the tasks that are ready to map for this particular mapper, right? And so we're gonna do this in a do while loop here, right, until this queue copy ready. While we're gonna keep looping as long as there is a queue copy ready event that exists, and what this race is actually, or what this code is actually doing here is protecting against a race where the scheduler might be actually called several times from different places, right? And so we want to handle the case where if there is duplicate calls into the scheduler at the same time, we don't want them each sort of racing with each other to call into the mapper at the same time. And with different state. We want the mapper to see like sort of a consistent state for the set of ready tasks, right? So what we do is we again take this queue lock, which is protecting, all of the mapper states and all of the, the list of ready tasks for each of the mappers, right? And we're just going to do a check to see if we're the first one in here, right? And if we are, right, we're effectively going to check this queue guard state, which says, are we the first ones in here to actually like swap off like the state of the queue? If so, we can set the guard to prevent other people from doing it, right? And then grab our copy of the queue. If not, we make a waiting event, effectively to say we're going to wait for the results of whoever else is doing in here at the same time, and then we're going to effectively come back around here and wait for this here, and then we can try again to grab the set of the state, right? And we save ourselves effectively. If we're the first waiter, we make the event to wait on, and then we save the event to wait on, and then we go back around the loop and we wait again. And eventually we'll get in here and we'll actually come down this path where there's no queue guard. And then we can, swap off the queue and make a copy, pull it onto our local stack, right? And then set the guard to prevent other people from jumping in here, right? So by the time we exit this while loop, we've got a copy of all the ready tasks for this particular mapper, and we've set the queue guard bit to effectively say like no one else can do this process until we're done doing this. Okay. So
hey Mike, I have a question here.
Yeah.
I guess you said something that made me think. So mappers have the different synchronization models, right? And I guess I would expect to sort of see that here, or is that
you're going to see that in the mapper manager object, which we will get to today. But the synchronization guard for like the synchronization mode for the mappers is all going to be handled by this mapper manager. So we're still kind of in runtime land here, but we will definitely talk about the synchronization mode and how. What you're going to see is this mapper manager is actually a virtual interface, and there's several kinds of mapper managers to handle the different synchronization models. Yep. Okay, so once we exit this, what we've got a copy. We effectively pulled a copy of all the ready tasks for this mapper onto our stack, right, and separate it out from the main data structure. Right now, other tasks can still come in and register. New ready tasks might still be arriving at the same time that we've pulled off a copy, into our local state, and that's okay. We'll see how we merge those lists back together later, but effectively we just have a sort of a consistent copy of what this queue looks like, so we can actually pass it to the mapper and not worry about it changing and stuff like that. Okay, the first thing that we do here is, as part of the scheduling process, mappers do have the ability to do stealing, and like effectively we want to do the stealing calls, the same time we do the scheduling calls if they're available. I'm actually going to bypass the stealing stuff today because it's not particularly relevant for a lot of applications at the moment. So we're going to skip this part today, but just notice that it is here. We are going to ask the mapper to do any kind of stealing work that it wants to do as part of the scheduler, right? And we do that before checking if this queue copy is empty, right? If the queue copy is empty, then we can, immediately go back around to the next mapper and keep going. Okay. But in the common case, we get down here, right? And so now we're going to ask the mapper which tasks does it want to map, right? And so we ask the mapper, so effectively these are the input and outputs to select task to map, right? And so these are mapper data structures that come from legionmapping.h that are visible to, to the mappers. And so we need to populate these data structures before we do the mapper call, right? And so right now we're actually like populating all the stuff into this input. Into the input data structure, so telling it which tasks are ready. Note that we're going to keep a copy for ourselves today. I actually think we could I need to check the data structure type on ready tasks. We might actually be able to optimize this just a little bit looking at it now, where instead of having to push all these things onto the back, we don't actually need to keep our own copy around because we know this input is invariant. So I might take a look at optimizing that. But for now, we're pushing the list of ready tasks into the input so that we can pass that off the mapper. Right, and so now we do the mapper call. And all mapper calls will look like invoke _ something and then the name of the mapper call in the mapper manager class, right? And we pass in our input and our output that goes off to the mapper manager. And when this method returns, right, we effectively have our output from the mapper as a result of this mapper call. Now, I'm not going to show you what this does right now, but we are going to go look at this today to see where this invoke select task to map call goes. So keep this in mind. We'll go take a look at where that goes off to later. But when we come back, at this point, we now have a list of tasks that are ready to map and a list of tasks that are ready to relocate to other mappers the mapper has told us about in this output data structure, right? Now, the first case that we handle here is actually the very unusual case where the mapper told us not to do anything with this particular thing. And right now, what you'll notice is that, this actually, what we do now is we expect, if in this particular unusual scenario where the mapper has told us not to map any tasks or relocate any tasks, we kind of expect them right now to actually have made what we call a deferral event to tell us when to run this mapper again. Right, and so we actually raise an error if they did not give us one of those deferral events. And the reason for that is that, effectively, if you don't give us a deferral event and you didn't tell us to map any of the ready tasks or relocate any of the tasks to any remote nodes or remote mappers, what's happening here is like we will actually end up going back around the scheduler loop again and again and again. And the scheduler actually has a pretty high priority at the moment in terms of its running. And there are actually ways that you could actually starve out other stuff from happening if you actually let the mapper sort of spin on select tasks to map over and over and over again. And you might starve work that is actually important to getting done. And so we kind of, as a safety at the moment, modulo having a better way of doing this, right? We kind of request the mapper set this deferral event, which we can actually we can effectively defer the scheduler based on this, event that the mapper has given us to tell us not to try to run the scheduler again, in this particular case, until this deferral event is actually ready, right? And so, but if they did give us a deferral event, well, then we can add that into our mapper state. We're going to put, effectively set that deferral event to be the thing to wait on, right? We're going to put all of our stuff back on the ready queue, right? This is if the ready queue was empty, right? If the ready queue actually was populated by new tasks, right, since the time that we actually did the mapper call, then we can actually follow through and go back around this loop and try and effectively allow the scheduler to call the mapper again because the state has changed, right? And so that's often a reason that we will reinvoke select task to map even though the mapper asks us to wait if the state changes, right? But if it didn't change, then we're effectively decrementing our active mappers because this mapper is no longer, an active mapper. It's given us a deferral event, right? We can put our stuff back on the queue. We can remove our queue guard, right? And then we can, trigger any queue waiters that were waiting, back up here in this do while loop before, right? And then defer our scheduling again for the future, right? And this is a pretty unusual case. Not many mappers actually use this deferral event, but I did want to explain the logic for that just so that you're familiar with it. Now, the much more common case is this else branch here, right? Which effectively we've got some tasks that are either ready to map or tasks that are ready to actually be relocated, right? So if we had any map tasks array, we put them in this selected set, effectively the tasks that are ready to be mapped locally. If we had any relocated tasks, we effectively look through these and make sure that the processor that they asked us to send them to is a valid processor kind. We don't let you put anything on utility processors, right? We also put those in the selected tasks, right? And then we can pop out of this else statement, right? And so now what we do is, for our local copy of all of the tasks, right, we effectively remove everything that was in the selected list, right? And some of this code could probably be optimized a bit, but it's actually surprisingly not run very, very frequently compared to a lot of the other stuff. So I'm thinking of ways to optimize this even as I'm describing it to you. But effectively, we pull off anything that's in our copy. If it's been selected, we remove that from our queue copy that we had before, right? And we put it in this to trigger data structure. And at this point, we actually end this particular block right here. Which I think is blocking, which effectively this if, was it that if? No, that was the if else statement. Which one is this ending? Right, that was ending not the do while loop. I think it's the end of the mappers, right? So by the time we get out of this particular block here, what we've got now is a list of tasks that are ready to either, that are ready to trigger, right? So I think it's let's see, if I come up here to this list of all the things up here, where is this thing happening? I'm blocking on what we're pulling out of the end of this. It's hard to tell. This is one of the problems with long functions. You can't tell exactly where things ended. Oh, we're still in the mapper loop, so we're still iterating over the mapper. Okay, so Okay, so I'm just going to keep going here. We're still inside of like, doing something for one individual mapper, right? And so, okay. And so now we need to put any tasks that were not selected, right, not ready to either to be sent remotely or sent or mapped right now, back on our ready queue, right? And so we retake this queue lock, we update the mapper state. If our queue copy is not empty, right, we put if the original queue, right, the mapper state ready queue, our queue, is not empty, we put our other stuff back on the back of the queue. Or back onto our queue copy, and then we can swap these things out because effectively we've merged the two lists, right? If this is actually if this is still empty, right, at this point, right, then we can actually decrement our active mappers, assuming there isn't a deferral event. And now we can actually do the triggering for these tasks, right? So for each of these tasks, we can get their context, and we can update their context state and effectively say we're going to map these tasks, for each of these two trigger tasks, right? And that allows us to actually decrement these active contexts, right? Assuming you've got enough own tasks outstanding, right? By decrementing the number of tasks that are now going to be mapped, right? If that goes to 0, then you can actually decrement the active context and change the state of the scheduler. Let's see. I'm going to ignore the stealing stuff for now. And again, on this path, we still have to remember to, effectively remove this queue guard. Notice we're still holding the queue lock from up here. So it's still safe to touch all these things, right? And make sure we wake up any other waiters that are waiting to come into this queue. Okay. And now, once we've done all that, right, before we, finish with this mapper, I think this is the end of the for loop for this particular mapper. Right now, we can actually trigger all of these tasks that are ready to be, woken up. Right, and so if it's a relocatable task, right, then you can actually send it remotely. You can update the target processor, and then you can mark that this task is no longer an outstanding task because it's going to be mapped. And then you call this task trigger task args, which actually sort of starts the next stage of the pipeline for this particular task. Right, so trigger task args is what we'll call trigger mapping. Right, to actually start mapping this task and actually start running it. And if it's remote, it will actually send it remotely. Right, so by updating, by updating this target processor, that will call the mapping of this task to move it to a remote node and register it with the mapper over there on that remote node. And then it'll go through this mapping phase again. But you do the same thing whether you're mapping remotely or sending it or mapping locally or sending the task remotely. They all go through the same path. And then down here, there's some more work for stealing, effectively issuing, if we had tasks if we still have work that's ready to do, we can issue advertisements and send any steal requests and stuff, but I'm going to ignore the stealing stuff for today. But this is effectively how we, how you pull things off. And by the way, this end bracket here is where we go back around and do the next mapper ID, right? And so we can do this for each of the mappers that are effectively active inside of this particular processor. Okay. So that's the scheduler. I hope that's much less confusing than what I described the last time. But effectively, this is the core of the scheduling logic. It's what decides, which task, effectively allowing the mapper to decide which task to get to map, and then either, mapping them now or kicking them off to map now, or actually, sending them to a remote processor to be mapped over there. So what I want to do now is actually, if there's no questions, now is a good time to ask a question because what we're going to do next is actually jump into this invoke select task to map API call here and see where that goes off to. So any questions before I move on to that?
So the queue copy, once you obtain the queue copy, I assume its size is fixed for the duration of that loop?
Yes, for the duration of this particular loop, yes.
So then I noticed that at least one container, one vector is being populated by doing pushbacks.
Yep. Yeah.
I think maybe I'm not trying to be pedantic here, but since we want to gain every bit of performance, you can do on the vector a reserve on the size and then...
Yeah, you could. Yep. In fact, that's what I was kind of looking back. I think this could actually I actually think we could pull this input actually up here above this do while loop, and we could actually just probably copy, just do the swap right onto the input thing here. I actually think that would be probably the most efficient thing to do, and I will actually probably do that later today. Looking at it now,
Yeah, because
yeah,
or even a simple reserve. Because if you do a reserve, then you avoid
right. Then you do the one memory allocation. And,
reallocations.
yes, yeah, and this really probably doesn't need to be a list here. So anyway, I will optimize some of that stuff. Like I said, I've actually, I mean, there are lots of, it's unclear how much performance overhead we're actually taking here. I've never seen like the scheduler call that comes in and does all this work be particularly expensive. It's not like these lists are terribly big, and it's not like we call this very, very frequently.
Yeah, so the queue is not big, and I assume the content, the elements are not that big.
Yeah, well, they're all pointers and stuff. So like, so yeah, the elements are tiny, and the queues are not big. So we're talking about small things here, but yes, right. I do agree with you in principle. Yes.
Yep.
Yep. Okay, I'm gonna jump to talking about this select task to map, and actually looking at the mapper managers and stuff for the rest of the talk today. So let's actually take a look at where this invoke select task to map goes to. So let's pop over here. I'm gonna pull up this mapper manager.h class over here. Okay, so a mapper manager is effectively a wrapper around the mapper object that the client will give us, right? So when you start up your Legion program, right, you get a default mapper, and you can also register your own mappers with the Legion runtime to make mapping decisions and stuff like that. And so, every mapper manager is just a wrapper around a mapper that we've been given by the application, right? So the actual mapper object itself is one of these mapping. This is the mapping namespace, right? And this is the mapper interface class, which is a pure virtual interface that every mapper implements, right? And this is your pointer to that particular object, right? And so a mapper manager is just a wrapper around that, and it knows, it's got a reference or pointer to the runtime, and it's got a mapper ID for this particular mapper. It has a processor that it's associated with, right? And there's a special, a little bit of logic here for whether this is a default mapper, right? Now, what you'll see here is that, in order to call a mapper API call, we have an equivalent method here in the mapper manager that effectively is the thing that you can invoke from inside the runtime to call all the different mapper calls, right? And so they all have the same standard, invoke underscore and then the name of the mapper API call that you might call in the original map, in the actual mapper interface to actually do those things, right? And the arguments here are, we actually take some more arguments here than what like the actual mapper call will get, but you also see like the standard mapper, structures here for the inputs and the outputs for each of these things. And so there are lots of mapper API calls that you can do, but they all have the same structure. And they all have, they all effectively come through sort of the same style with like, an operation and an input and an output structure for the things. And then, sort of one of these mapping call infos, which we'll talk a little bit about here in a minute. Now, one important thing to notice about this mapper manager interface is it actually is there are some virtual calls in here. Notice that the invoke calls are not virtual. They're the same, for all mapper managers. But there are some virtual methods here, right, associated with like testing whether this is a reentrant mapper or not, enabling and de-abling reentrancy. And most importantly, these four methods right here are actually probably the four most important ones to pay attention to here, right? Effectively, the calls to begin the mapper call, to pause it, to resume it, and to finish a mapper call, right? And there are actually going to be different implementations. There are two different implementations of this mapper manager class. Right, so let's actually scroll down here, and there's a whole bunch of stuff in this mapper manager class, but there's actually two different instantiations of this mapper manager class, right? The first is a serializing mapper manager, right? And in the mapper interface, mappers can sort of request that they have different synchronization modes they can request of the runtime, right? So just for familiarity, let me actually just for people that might not be familiar with this, let's actually take a look at the mapper class, just to show you what I'm referring to. This is actually the mapper interface class itself. So here's our base mapper class, right? And one of the first things that mappers do is they select their synchronization model, right? And they can effectively pick from one of three different synchronization models, right? They can either pick, concurrent, which means that you can have multiple mapper calls coming into this single mapper object all at the same time, right? And sort of the mapper itself will do its own synchronization using, by locking and unlocking the mapper. Or you can have these serialized modes, right? So serialized reentrant means that at most one mapper call will be calling, or at least one, call into the mapper object time will be done by the runtime. But if like a mapper call preempts in the middle, doing something else, right, then the runtime can call in with another mapper API call, right? And then there's serialized non-reentrant, which effectively says that each mapper call done by the runtime into this mapper has to finish before you can start the next one, right? And so we have to support these different synchronization models, right? The runtime is only allowed to, right, in this mode, in current, right, the runtime can call in as soon as it's ready to do whatever it needs to do. Right, in these other two, it needs to sort of do some extra work to make sure that it's safe to actually call into the mapper before it's allowed to actually start. Right, and so the implementations of where are these four? The begin and end. Actually, we can see them down here. Implementations of these four methods right here are effectively what are going to determine the behavior of beginning and ending mapper calls, as well as pausing in the middle. We'll talk about pause and resume here in just a minute. But so you can see we have a serializing mapper manager, and it actually has a bit to say whether or not you permit reentrant calls in here, and if so, that's effectively handling this will handle each of these two cases, the serialized reentrant and the serialized non-reentrant modes, right? And then there's a concurrent mapper manager, right, which effectively handles the case where you can pretty much just, what we're going to see is that these calls actually don't do a whole lot because you can effectively call right in right away, right? And then the more interesting thing is some of these like locking and unlocking mappers will be more interesting in the concurrent one. Whereas, effectively the lock and unlock the mapper in a serialized mode is effectively a no-op because, you don't have to do anything. You've already handled the serialization, with these begin and finish and pause and resume mapper calls. Okay, so let's actually take a look at we'll actually follow through select task to map and just see what that mapper call actually looks like. So let's actually pull up mapper manager. .cc. Okay, and let's call vote select tasks to map. Okay, so here we're in the base mapper manager class. We get our call into select task to map. We've got some input, some output. This mapping call info is initially null the first time that you're calling into it. You're going to see a lot of these continuations. I'm going to ask you to ignore those today. They actually need to be refactored and made to go away. So really what's happening here is we're coming into this statement, right? This info is null, so we need to get a mapping call info, and I'll describe what this is in just a minute. But you notice we're going to get this, we're going to call begin mapper call. It's going to give us back one of these info things. And then let's assume that we get it and there's no continuation precondition. So we can skip this if block, which will eventually disappear. Right, at that point, we can actually do this call into select task to map to actually perform the mapper call. So that's actually the API call that goes to the mapper itself and actually talks to the mapper object and actually performs this call, right? And when we return from this method, right, then we can call finish mapper call, right? And so, every mapper call will say begin mapper call, and then do the actual mapper call itself, and then call finish mapper call when it's done. And you'll see this is true in pretty much every single one of these API calls. There's a begin, a mapper call, and then a finish, right? And this is true of pretty much all of them. And so the same pattern is repeated. The important thing that you need to do is you need to make sure that this begin mapper call with this info actually is ready to start, and that's what this continuation precondition is testing. So really what should really happen is there should actually be a wait here if we're not actually ready to do this. These continuations are really mostly unnecessary, but they're still functionally correct. You still do need to block if this mapper call is not ready to start with this info. So let's actually go look at begin mapper call and actually see what happens. And there's two different versions of this, right? There's the one for the serializing mapper manager, and there's the one for the concurrent one. We're actually do the concurrent one first because it's simpler, and then we'll talk about the serializing one. Right. So the concurrent one is actually really simple, right? So we're going to call allocate call info, which will give us one of these mapping call info objects. If we're doing any profiling, we effectively turn on we record the start time for this particular mapper call, and then we're done. It's actually quite simple. And if you look at this allocate call info, right? It's actually just creating one of these mapping call infos, which is effectively just a way of recording, what is the mapper manager, what kind of mapper call are we doing, and which operation, is associated with this particular mapper call. And that gives us a little bit of state associated with this mapping call info object. And this, for those of you that, just to, to make it terribly clear what's happening here, is this mapping call info thing here is actually, if you look at most mapper calls, like if we look at select task to map, right here's select task to map, you get one of these mapper context things. This pointer, this mapping call info pointer, is actually one of these mapper context things, right? So this is just and I can let's actually make this very obviously clear what's happening here. But if we look in Legion types .h and we search for mapper context, right, you can see inside the mapping namespace, we just have a little type def here that's going to type def this mapping call info into the mapper context, right? So a pointer to a mapping call info is what we consider a mapper context object, which every time you do a mapper call, this helps us, gives us know where we are whenever you're calling back into the runtime from inside the mapper, so we know what's happening. We'll see some cases where that's actually used. Okay, where do we go? Yeah, okay, so allocate call info is just making one of these mapping call infos, creating a little context object, right, and begin mapper call. Right, so begin mapper call was very simple for the concurrent one, right? But for the serializing one, it's actually a little bit more complicated, right? So the serializing one, we actually have to make sure it's safe to actually start our mapper call, right? It's not actually safe if there's already a mapper call happening, right? Either whether it's whether it's actually running or is blocked on something else. If it's not reentrant, then we may also need to wait to start our mapper call, right? So we allocate a call info the same way the concurrent one does in the serializing mode, but then before we can actually start, we actually have to take this mapper lock, right? And there's a bunch of state that actually goes on here to see, like, is there something else happening, right? Check to see if there's like so there's a bunch of intermediate states here associated with like mapper calls that are sort of in intermediate states. I'm actually going to skip these first two, but let's actually do these, describe what's actually happening here, because these are actually important, right? So, check to see if there is an executing call, right? If so, we're going to need to make an event, right, to tell us to wait on, and then have somebody else wake us up with that event once that prior executing mapper call is actually done running, right? So pretty much everything in here is checking to see, if there's an executing call, or if we're not allowed to do reentrant, and there's a pause call in place, right? Or there's already ready calls that are, ahead of us in line, right? Then we have to put ourselves on the list of pending calls, right? And so we give ourselves an event to wait on to be triggered when it's ready to wake up, right? This becomes our precondition that comes out of this begin mapper call, right? Is effectively the event that will tell us when it's actually safe to start, right? If we've been told to prioritize this mapper call, we put it on the front of the pending calls, right? The next one to wake up. If we've been told not to prioritize, then we put it on the back, right, to effectively wake it up in order, right? But if neither of these are true, then we can make ourselves the new executing mapper call, sort of put ourselves as like the current executing mapper call, right? And then we can actually start running. Now, there's this toTrigger here is handling some intermediate cases where we might actually need to do some like forward progress work to wake somebody else up. I'm actually not going to cover some of those more intermediate complicated states today, but we can talk, like I'm happy to answer questions offline about sort of these pending pause and pending finish calls. Like there's some intermediate states here where we do some tricky stuff with locks, but that's effectively like what's kind of happening here. I'm hand waving a bit on that part, but the more common case here are these cases where either there's already an executing call in progress, or we're about to become the new executing call, right? And then we do some profiling work, which we can talk about later with the profiler and stuff, and then we can return our result. Similarly, right, if you look at finish mapper call, right, this is the finish mapper call that we do at the end of the mapper call, right? Like again, some profiling work, right? And then what we do is we effectively say that we're finishing our mapper call, and then we can grab the lock, we do any work to clean ourselves up and trigger any future waiters that are ready to start running, right? And then we can trigger that event once we've released the lock, and then we call free call info, which will actually just clean up this context object here. And similar things happen on finish mapper call for the concurrent mapper manager, right? And there's some interesting things here, like, this is actually in the concurrent manager, like if someone exits the mapper call where they're still holding a lock on the mapper, then we help clean it up for them and stuff like that. I'm mostly ignoring the concurrent mapper manager today because it's actually less commonly used, and also it's much simpler. So like, I feel like you guys can work through, the concurrent mapper manager version on your own. It's much simpler and easier to understand than the serializing mapper manager, which has more state and has to do more, sort of synchronization for clients. Okay. So the other thing that can happen, right, is inside of these mapper calls, right, when you call it to a mapper, where's the mapper API, right? So when you do a call to...
Can I ask a question?
Yeah, go ahead.
The serializing.
Yeah.
Wouldn't a reservation, could this say the reason why you're doing all this stuff with the events and everything is so that two mapper calls on the same mapper cannot execute concurrently, right?
That's correct.
And
yes.
It looks like you're achieving this by, like, if a call comes in and there is, like, somebody is executing, then I'm gonna put myself in a queue.
You're
right?
putting yourself in a queue and then giving an event to trigger when you're ready to wake up, right? And eventually you'll sleep on that or wait on that event.
Mm-hmm. Right. Isn't there couldn't this be achieved with like realm reservations or something like that? Like have all of the mapper calls.
Yeah.
And they're all separate tasks, right? So
I mean, you could do this with like a reservation where like you effectively you could ask to acquire the reservation on the mapper, right? And then you could effectively wait if you don't get the event or don't get the reservation, right? You get an event back and say like, okay, I'm gonna go to sleep on that event. The one thing that's not so good at is like that sort of leaves it a little bit up to chance a little bit as to who gets the reservation and stuff. So we're actually doing a little bit of like a little bit more intelligent stuff here to sort of do our own user level scheduling almost on top of Realm. To try and manage like the order in which these mapper calls happen, right? So there are ways to like prioritize certain mapper calls, which are important, right? So we can actually like put those at the front of like the pending calls and stuff. So we're definitely managing this ourselves a little bit instead of leaving it up to chance with the Realm reservation to decide, who gets the priority to run next.
Okay.
And that's a choice. Yeah, I mean, you probably could implement this with a reservation, and it'd just be less like you just be more at the randomness of like Realm synchronization, Realm reservations to decide which order to do things in.
Has this happened in other places as well where you needed to do your own?
No, not so much, because the runtime can manage its own stuff internally a little bit better. But like with the mapper calls, like different mapper calls come from different stages of the pipeline, and often you want to prioritize certain ones more than others to help drain them out. And so that's sort of the reason that I decided to do sort of my own scheduling here.
Yeah, thanks.
Yep. Okay. So one other thing that can happen, right, inside of a mapper call, like if I call select task to map, right, there's a whole bunch of API calls down here that the mapper can actually do to like actually ask the runtime various different things as the part of a mapper call, right? So like lots of these, there are lots of calls, like, and this is true of every mapper query that we do, or every query that the runtime does, the mapper can turn around and call back into the runtime and do things like, I don't know, test index spaces overlap, create physical instances, doing acquires, looking at task variants and stuff like that. And you notice that all of these take a mapper context object that they pass back into the runtime, right? And so if we actually go look at, let's pop this up here and go look at legionmapping.cc, right? So if we do something like, just to give you an example of a call that you guys are probably all familiar with, like, if you do create physical instance and call back into the runtime to actually create a physical instance with a mapper context, right? You can see that this is where we use this context object to call, to get the mapper manager, and then call create physical instance on that mapper manager. So if we actually pop back over here to our mapper manager and look at create physical instance. And I'm not saying this is an example of like an API call that you would do like inside of select task to map, but this is an example of calling back into the runtime from the mapper. Right, we do a little bit of sanity checking here on some of the arguments just to make sure that we're going to actually do stuff. But before we can do anything that might eventually end up blocking, what we end up doing is we call pause mapper call, right? And this is effectively the point where we say, okay, we're crossing the boundary from the mapper, or from the mapper back into the runtime at this point, right? This pause mapper call, and we might end up blocking or doing some other work in here that's really expensive. And so we need to effectively stop our mapper call in case we end up blocking. And then we can, like, any waits or anything else that might occur in here, like lock acquires or anything else that occurs inside this function will not, deadlock our mapper because we effectively mark that we've left our mapper. Right? We go off and we do some runtime work. We're not actually going to look at this work today. But then we call, and then when we're done with all of our work, associated with this call back into the runtime, then we can call resume mapper call, right, with our mapper context, and then we can return once we've done that. And you'll see all the calls back into the runtime have the same pause, do our stuff, and then resume mapper calls. Right now, if we look at pause mapper call, first off, for concurrent managers, right, there's nothing to do, right? Like for these cases, effectively, there's no reason, we're not managing any synchronization state for these concurrent managers, so there's really nothing for us to actually do here, right? But in the serializing mapper manager, this is where things get more interesting, right? So effectively, we should be the current executing call info, right? So we can effectively mark that we're about to do a pending pause. We grab our lock, right? We effectively see if anyone else has done any work to wake ourselves up. If not, then they will, like, effectively this pending pause gives people permission to actually, like, change this executing call info thing, and if necessary, we do any work to wake up anything that's effectively ready to run. Like if we actually look at complete pending pause here, right? This is where we actually do all the interesting work to say, we're the first ones to get into this pending pause call. If there are any, we increment the number of pause calls. If we're allowing reentrant, then we have to wake up, anybody that's pending first, right? So any calls that, had already started running but had paused previously, then we're going to wake them up, and we'll actually, return the event to actually trigger, to actually do that wake up. Otherwise, if there's no calls that were paused that are ready to run now, then we'll actually look at the set of ready calls and pop the first one off the front and actually run that. Right, and then we can mark that we're no longer the executing calls, right? And so that's effectively how you wake up sort of a waiter as part of pause mapper call. And if you do any event triggers, we try not to do event triggers while holding locks. That's not always entirely true, but I try to maintain that invariant. And so then in resume mapper call, right, it's actually the opposite, right? You effectively are saying effectively, are there any pause calls? If so, let's see. There should be at least one pause call, right? We should at least be one of them, so we're going to decrement that, right? If there's already an executing call, then we need to effectively put ourselves on the list of ready calls that are ready to wake back up, right? Give ourselves a ready event to wait on when we're ready to be triggered. Otherwise, we can resume right away and effectively make ourselves the current executing call, right? And if necessary, we have to wait on this event to know that it's safe to actually resume, right? And then we can actually return from this method and actually start running again, right? And so the serializing mapper manager effectively guarantees that it effectively provides all the synchronization guarantees that that the application or the application manager is actually the client mapper is actually expecting from us based on these synchronization modes. And so, pretty much anytime you want to look at these mapper calls, either calling from the runtime into the mapper or from the mapper back into the runtime, you want to look for these 4 sort of, begin mapper call, pause mapper call, resume mapper call, and finish mapper calls, right? And as long as you just put these in the right places around your stuff, pretty much the right things should happen. So, and these should be mostly invariant to pretty much any kind of, any kind of mapper call that, we might add in the future, any kind of call from the mapper back into the runtime. Just make sure you always look for adding the right calls in the right places, depending on which direction you're going in each of these things. Okay. So with that, let's see. I have one more topic to cover today since we have a few minutes left, but I want to stop here and see if anyone has any questions before I do the last little thing, if we have time for it. No questions. Okay. So hopefully this makes sense about how mapper managers work and how mapper calls actually end up getting executed and maintain their invariants with actually talking to the mapper. Okay, so let me actually show you guys one more thing here. So we looked at some of these. This is sort of a digression, but it's an important one because it's going to show up a lot throughout the rest of our calls here. So like this finish mapper call, or actually let's look at resume mapper call because it's actually a wait here. So one of the interesting things about, I want to point this out because it's actually very important. So this is waiting on an event, and in particular, we're waiting on a runtime event here. Effectively, a runtime event is one that at the moment cannot be poisoned, right? So, right, I think I've mentioned previously, there are runtime events and application events, and Legion enforces a pretty strong type distinction between, the application events are completely separate from the runtime events, right? Application events have to do with actual application realm, computation, and runtime events have to do with like Legion meta internal stuff, right? And so application events can be poisoned either because of faults or because of predication, but Legion runtime events and stuff can't be poisoned, at least not at the moment. And so we actually have this separate type distinction between runtime events and application events. But importantly, both runtime events and application events like this, are instances of what I call a Legion event or an LG event. Do we still have Legion types here? No, it looks like I closed it. Let's actually open it up here. Let's see. Yep. So what you'll notice is that Legion actually has its own event types built on top of realm event types. So this is a realm event, right? And a Legion event, LG event, inherits from realm event. And most importantly, it's actually going to override these wait methods, right? And we'll look at those in just a second. But then you can see the application event is a kind of LG event, right? And application user events are a kind of application event, and application barriers are a kind of application event, right? And runtime event is a kind of LG event. Same thing with runtime user events are a kind of runtime event, and runtime barriers are a kind of runtime event, and so forth. And so anyway, you can find all these things. But importantly, the really important thing here is that this LG event is inherited from a realm event. And it overrides statically, these are not virtual methods, but statically overrides the wait methods for every event. So if you wait on a Legion event, as opposed to, now if you wait on a realm event, right, it goes into realm and realm can preempt the user level task. Now in Legion land, right, if we actually search for this wait method here, you'll notice this is actually a pretty important method. And it's actually quite a bit more complicated than what you might originally think to wait on an event. And the reason for this is that there are some thread local variables that Legion maintains to help track things like the implicit context, right? And the implicit provenance for which task was running this thing. There's effectively there are very few, but there are a few thread local variables associated with various things inside of Legion. Some of these down here that are in macros you can mostly ignore, but there are a few important ones here, right? You have an implicit context that knows which task context is associated with wherever we're running. You have an implicit pointer to the runtime associated with each thread. You have a list of all the locks that are required. We'll look at this sometime later. But whenever you wait on a Legion event, effectively we save all these thread local things onto the stack, and the reason for that is that Realm can actually like preempt your when you actually wait on a Realm event, right? If you call Realm event wait, right, that might actually preempt your task, and when you wake up, you might actually be on a different hardware thread than the one that you were actually on when you went to sleep, right? And so, effectively, anytime you wait on a Legion event, we actually pull all of these thread local things onto your stack. We do any things. We'll talk about the lock list at a later point in time, but for now, you do the Realm event await, and then once you wake up, you can restore all your stuff that you pulled onto the stack back into your thread local variables and stuff like that. And this is true of both wait and wait fault aware. And so we do that for both of those two cases. But it's important to realize that like this is why you'll never see any naked Realm events in a Legion program, is that effectively you want to make sure that if you're going to wait on an event like we do here in resume mapper call, right, this wait is actually doing all the things to stave all of our state and restore ourselves correctly whenever we wait on a Realm event. Now we don't like to wait very often, but there are cases where we do wait, and so you have to do the right thing in all those cases, right? And so the fact that we have these our own wait events here that save any thread local state that we've got and stuff is important to be aware of, that's what's going on behind the scenes, because Realm can and will preempt your task if you call wait, and it might thread switch it might do its user level thread switching onto your own onto a different kernel thread, right? So you've got to save any thread local state anytime that you wait on stuff. So anyway, that's just a little digression. We had some time for it here, and I wanted to point out because it'll be true of everywhere in the Legion program, and like I said, this is why you'll never see any naked Realm events. You'll always see an LG event or an RT event or an AP event everywhere inside of Legion to let you know what kind of event you're working with and that it's a Legion event and not a Realm event. Okay, so with that, we're at time. Any questions before we wrap up? Okay, great. I'll post the recording online, and we'll be back next week with a Realm session.